So quick recap of taking a log. Log of a number has two parts. One part is called the characteristic, the other is called the mantissa. The characteristic you decide, which is the number of places before the decimal minus 1. The mantissa comes from the table. Characteristic is count the number of places, subtract 1 from it. Mantissa, you look at the number without the decimal, the first two digits in the first column, the next in the next, and the last in the last column. The characteristic is always an integral value, while the mantissa is always a decimal value, is always written as 0 point something. So the characteristic here is 1 and the mantissa is 0.9524. So when you bring it together, it is 1.9524. That is the log of 896.3. We did this but in a table. Henceforth, we are not going to use the table. It should happen in your own brains. It should happen in your own head. The entire table should happen in your own head. And that is number of places before the decimal, minus 1. Look at the number without the decimal. Approximate the number. This you will do if it is more than a 4-digit number. Mantissa, you look for the table. First two digits in the first column, next in the next, and then the mean difference column. And this is the log, which is characteristic plus the mantissa. And this is what we got. Correct? So I want you to put that aside now, and with your knowledge of how to take a log, I'm going to elaborate a little. I'm going to use that knowledge. How am I going to use it? What I'm going to do is I'm going to take logs of a few random numbers and then define a few rules, define a few formulas and so on. So to begin with, henceforth, when I ask you to take a log of a number, will you actually draw the entire table? No. So if I ask you the log of, let's take a random number, 432.3. 432.3. How are you going to do this? Log of a number has two parts. One part is the characteristic and the other is the mantissa. Finally, it is characteristic plus mantissa. So let's write down the characteristic first. Number of places before the decimal is 3. 3 minus 1 is 2. This is the characteristic plus the mantissa. For the mantissa, I will look at the number without the decimal. So without the decimal, the number is 4323, 4323. So in 43, I have to look for 23. Let's start doing that. Let me zoom this a little. I think that should be enough. In 43, so let's come to 43 first. 43. We are looking for 2, 3. So this is 0, 1, 2. 6, 3, 5, 5. And in that I'm looking for 3, 1, 2, 3, which is also 3. So 6, 3, 5, 5 plus 3 is 6, 3, 5, 8. So this is going to be plus 0.6358. When I bring them together, the log of 432.3 becomes 2.6358. Let's take one more. If I take another random number, let's say I am asking you to find the log of 87.14. You will say 87. So 2 places before the decimal, minus 1 is 1, plus 0.8714. In 87, I have to look for 1. In that, I have to look for 4. In 87, I have to look for 1. 87 will be on the second page. So in 87, I have to look for 1. In 87, I have to look for 1. So 0, 1. In that, I have to look for 4. 1, 2, 3, 4 is 2. So it is going to be 9400 plus 2 is 9400. 2. So 9402. So bring that together, and the log of 87.14 is 1.9402. Is that right? But I have a question for you. And my question is, you say that the log of 432.3 is 2.6358. Or you are also saying that the log of 87.14 is 1.9402. Is that correct? These are the two log values that we found just now. I agree with you, I just found them. But I have a question. And my question is, what is this? Where is this coming from? What logic is it that you've used here? That when you say log of 432.3 is 2.6358, what do you mean? What does it mean that this is equal to this? I'll give you an example. When you say that when you say that 5 square is 25, what do you mean? What you mean is when 5 is multiplied 2 times, you get 25. There is a logic, no? And the logic is 5 square is 25 means 5 is multiplied 2 times. Am I right? Or when you say, let's say the cube root of 8 is 2. What does that mean? What it means is 8 has 3 2's in it. And since I'm taking a cube root, I have to make pairs of 3. And I bring 1 2 outside and the answer is 2. There is a logic. There is a logic that I understand. Or even if I ask you, what is, let's say 14 divided by 2? What is that? 7. What does that mean? You have to divide 14 into 2 equal parts. 7 and 7. 2 equal parts of 14 is 7 and 7. That is what it means. That is the logic that it is used here. What do you mean, or what is the logic when you say that log of 432.3 is 2.6358, or what do you mean when you say log of 87.14 is 1.9402? What do you mean? What is the logic that you are using here? Whenever a log is taken, it is taken to a certain base, or it is taken by keeping a certain number to the base. When the log sheet, or the sheet that has logarithmic values written in it, I have shared it with you. Do you notice there is a 10 here? And that 10 is in the base. So this is read as log of n to the base 10. Now here the base is not written. It's not written because it is assumed to be 10. So if all logs are taken to the base 10, why write it? No. All logs are not written to the base, taken to the base 10. Logs are taken to different bases. There are two most commonly used bases. One is 10 and the other is E. What is E? I had discussed E with you. E is an irrational number. It is a non-recurring, non-terminal number. That is why it is irrational. And because it's a very lengthy number, we don't write the value of E. We have given it a name. And the name for that number is E. Again, what is E? It's a number. The value of E, if you want, is 2.71828, and this keeps going on up till infinity. So because it is a non-terminal number, we don't write the actual number, we write it as E. Whenever logs are taken, they are taken to two bases. One is to the base 10 and the other is to the base E. Logs taken to the base 10 are the most commonly used logs. and that is why we call them common logs. If you look at the sheet that I had given you, doesn't the heading say 4-place common logarithm? Common logarithm because the base here is 10. Similarly, logs taken to the base e are called natural logs. Why they are called natural logs is for another day, not for now. So logs taken to the base e are called natural logs. So when you say that log of 432.3 is 2.6358, what it actually means is log of 432.3 to the base 10 is 2.6358. Wow, fantastic. But a problem, I still don't understand what this means. Even though you write down the base 10, how am I supposed to know what it means? Well, I'll tell you what it means. What it means is that if log of a number a to a given base b is a value c, if log of a number a to the base b is a value c, then what it means is when b is raised to c, you will get the value a. What it means is when b is raised to c, you will get the value a. This relationship between a, b and c is called a logarithmic relationship between a, b and c, and this relationship between a, b and c is called the exponential relationship between a, b and c. So if log of a number a to a base b is c, then b raised to a should give you, b raised to c should give you a. Then if log of 432.3 to the base 10 is 2.6358, then when 10 is raised to 2.6358, what should I get? I should get 432.3. When 10 is raised to 1.9402, what should I get? I should get 87.14. But sir, I want you to verify it. How do I assume that this is correct? I will prove it to you that this is correct. So, if log of 432.3 to the base 10 is 2.6358, then what it means is when 10 is raised to 2.6358, what should I get? I should get 432.3. Or if you say that log of 87.14 to the base 10 is 1.9402, then 10 raised to 1.9402 should give you 87.14. But sir, how do I verify that it is correct? Calculator. Check this in your calculator. You have to raise 10 to 2.6348. Sir, problem. In my calculator, I can raise 10 to 2. I can raise 10 to 3. I cannot raise 10 to 2.6358. Well, that's okay. I know you can't do this. I know you can't verify this. So you can either do this in your cell phones or you can try this in a scientific calculator. How? So I'm going to show you the same now, but in a cell phone calculator. So what you can do is you can use any phone for that matter, but needs to be smart. I'm using this phone. You can have any smartphone. The first thing that you do is you turn the rotation on. Auto rotate should be on. Once auto rotate is on, the next thing that you're going to do is open your calculator. This is your calculator, correct? After having done that, turn it horizontal. The moment you turn it horizontal, it becomes a scientific calculator. So you will see an extra set of buttons here. In that, now a few calculators, every calculator has its own set of buttons. Here you will see a caret sign. This is a caret sign. I'm sorry. This is a caret sign. Some calculators will have an x raised to y here, which does the same job. It's not different in any way. So let's find out if these calculations are correct. So one calculation at a time. First calculation says that when 10 is raised to 2.6358, I should get 432.3. Let's check. 10 is raised to, so press the caret sign. What is raised to? 2.6358 equal to, do you get a 432.31? Yes, 432.3. So whatever this logic was is a correct logic. There's nothing wrong with it. Let's check this. Cancel whatever is there on your screen. 10. Again, either press the caret sign or the x raised to y sign, whatever you have on your calculator. Raised to, it will automatically give you raised to. This represents raised to in technical language. 1.9402. 1.9402. Press equal to, what do you get? You get 87.1364, which is 87.14. And this is what it is. It is true. It gives me the same value. And this is how you can use a scientific calculator or a cell phone to verify if this is true. So the bottom line is, whatever calculation we have done here is a correct calculation, or this logic that you said you are using is a correct logic, which is, if you are saying that log of a to the base b is c, which means when b is raised to c you get a, or if you are saying that log of 432.3 to the base 10 is 2.6358, it means that when 10 is raised to 2.6358, you get 432.3. And this is the first log rule that we are going to do, and that is the exponential and the logarithmic relationship between a, b and c. I want you to pause the video and write this down, this along with this example. So write down the rule. Right after, wherever you've written the this explanation, right after that you can start writing this. So what we are going to do is, we are going to prove a lot of log rules as and how we are learning them, and then we are going to write all of them together later. So now you don't need to worry about it, just keep writing the explanation. So the first thing I want you to do is write this down, which is the log rule. This is the logarithmic relationship between a, b and c. This is the exponential relationship between a, b and c. After having written that, below that I want you to write this down. And that is the explanation of that relationship. Like when I say that log of 432.3 to the base 10 is 2.6358, it means that 10 raised to 2.6358 should give me a 432. These are the two examples. Pause it, write it down. I'm moving on. So now that we've proven this relationship, I'm going to do a few more and then I'm going to continue. So now if I ask you log of let's say the number 736.9 to the base 10 is what? I have a to the base 10 log table. Okay, if I have a to the base 10 log table, I can do this. How many values before the decimal? 3. Minus 1 is 2 plus 0 point. Number without the decimal is 7369. So in 73, I have to look for 6, and in that I have to look for 9. 7369. So in 73, I am looking for 6. And in that I have to look for 9. 5. So it is going to be 8669 plus 5. So it is going to be 8674. So it is going to be 0.8674. Let me check that once again. 7369 under 73. We are looking for 6. And in that we are adding 9, which is 5. So it is 8669 plus 5 is 8674. So 8674 is correct. Let's finish that off then. Then log of 736.9 should give you 2.8674 to the base 10. What does that mean? Well, what it means is when 10 is raised to 2.8674. 10 is raised to 2.8674. I get the value 736.9. You don't believe me? Let's check if that is true. Let's come back to our cell phones. Open the calculator. Shift it to a scientific calculator. Let me zoom that in a little for you. So 10 raised to the x raised to y button, 2.8674. Press equal to, you get 736.88, which is approximately 736.9. So it is a correct logic. Then can I say this log rule is understood? There's no problem with it. What I want you to do is, I want you to look at this carefully. So what is this log table? This log table is nothing else but powers of 10. Is that right? What are you trying to find? When I ask you the log of 432.3 to the base 10, what am I asking you? I'm basically asking you, what should I raise 10 to get 432.3? Isn't that what I'm asking you? So isn't this table nothing else but powers of 10? Powers of 10 that will give me the value 432.3. So let me ask you a very basic common question. You are asking me what should be the power of 10 so that I get 432.3. So I'll tell you one thing. 10 raised to 1 is 10. No, I am looking for 432.3. 10 square is 100. No, I am looking for 432.3. 10 cube is 1000. So 10 square is 100, 10 cube is 1000. So 10 raised to 2 is 100, which is smaller than this. And 10 raised to 3 is 1000, which is greater than this. Then can I say the power that I am talking about should be between the second and the third power? And that is why it is somewhere between 2 and 3. It is 2.6358. Let's come here. When I ask you the log of 87.14 to the base 10, what am I asking you? I am asking you what should I raise 10 to get the value 87.14. 10 raised to 1 is 10, 10 raised to 2 is 100. So 10 raised to 1 is smaller than 87 and 10 raised to 2 is greater than 87. So the number should be somewhere between 1 and 2. Yes, it is 1.9402. Do you notice it is 1.9, which is very close to 2? You know why? Because 87 is very close to the second power of 100. It's very simple. I want you to grab this knowledge as much as you can. I want you to put this into your knowledge base. I want you to understand what a logarithm is, so that log rules and then when you are applying logarithms becomes much easier. For the last time, when you ask me what is the log of 736.9 to the base 10, again 10 raised to 1 is 10, 10 raised to 2 is 100, 10 raised to 3 is 1000. 100 and 1000. This number is between 100 and 1000. Then the power should be between the second and the third power. That is, the power is 2.8674. So you are basically, whenever you are asking me the log of a number to the base 10, you are basically asking me what should I raise 10 to get the number 736.9. So I should raise 10 to 2.8674 to get the number 736.9. I hope this is understood, because I'm going to elaborate on this a little more. So if you've understood that, when you are asking me the log of 736.9 to the base 10, you are basically asking me what should I raise 10 to get the number 736.9. Then can I ask you something? What is the log of 100 to the base 10? 100, 3 places before the decimal, because then the decimal is here, it is 100.0. 3 minus 1 is 2 plus 0.100. Without the decimal, this number is basically 1000. So if I am looking for 1000 in my sheet, 1000 is going to be 10 and 0, 0, 0. So 10, 0. And then because it's 0, there is no further bifurcation. So 10, 0 is basically 0, 0, 0. Fine, then it is going to be, the mantissa is going to be 0.000. So my answer is 2.000. So the log of 100.0 to the base 10 is 2.000, or in other words, the log of 100 to the base 10 is 2. But did I need this to tell you that? When I ask you what is the log of 100 to the base 10, I am asking you what should I raise 100 to get 10? Or, sorry, what should I raise 10 to get 100? Or in other words, I am asking you 100 is which power of 10? 100 is the second power of 10. Then the answer is 2. 10 raised to 2 is 100, or 10 square is 100. Then do I need to do this ever again if at all the number is a power of 10? Like for example, if I ask you log of 1000 to the base 10, am I stupid to use the log table? No. What should I raise 10 to get 1000? Or 1000 is which power of 10? 10 raised to 1 is 10, 10 raised to 2 is 100, 10 raised to 3 is 1000. 1000 is the third power of 10. What if I ask you what is the log of 10,000 to the base 10? Well, simple. 10,000 is 10 raised to 1 is 10, 10 raised to 2 is 100, 10 raised to 3 is 1000, 10 raised to 4 is 4000. And that is why the answer is 4. So, do I always need the log table? No. If this value is a perfect power, then I don't need a log table. Then can I elaborate something? And can I say, if I ask you the log of 10 to the base 10, what will I get? Log of 10 to the base 10. Isn't 10 the first power of 10? The answer is 1. Why? When 10 is raised to 1, I get 10. Which brings us to another rule. Question number 1. Does the base always have to be 10? No. Not compulsorily, not necessarily. I will show you more examples where it might not be 10. What if it is something different? Whatever it is. If I ask you what is the log of 25 to the base 25? So 25 is the first power of 25. Then the answer is 1. What is the log of 14 to the base 14? 1. What is the log of 16 to the base 16? 1. What is the log of 15 to the base 10? This I can't tell you. Because 15 is not a direct power of 10. 25 is the first power of 25, 14 is the first power of 14, 16 is the first power of 16, and so on. 10, The first power of 10 is 10. The second power of 10 is 100. 15 is between 10 and 100. So the answer will be 1 point something. My problem is I can't tell you the exact value. I will need a log table. But for this, do I need a log table? No, because it's common sense. Every number is the first power of itself. So in a generalized form, if I ask you log of a to the base a, log of a number to the same base is always and always 1. So the answer to this is going to be 1. I want you to come back and write this down with an example. And the example is, if log of, let's start from here. If log of 100 to the base 10 is 2, then log of 1000 to the base 10 is 3. Why? Because logs are nothing else but powers of the base. The base here is 10. I am asking you, what power of 10 will give me 1000? Well, the third power of 10 will give me 1000. So if I am asking you log of a number to the same base, well, the number and the base are the same, which means it is the first power of each other. I don't need a log table to do that. So if I ask you, what is the log of 25 to the base 25? 1. 14 to the base 14? 1. 16 to the base 16? 1. Because log of a number to the same base is always and always 1. So I want you to come back and write this down, and below it I am dictating. Write that down. So if you want, pause the video, write it down up till here, and then write down whatever I am dictating. So what you are going to write down right below this rule is that log of a number to the same base, log of a number to the same base is always 1. Log of a number to the same base is always 1. So log a to the base is 1, log x to the base x is 1, log p to the base p is 1, log q to the base q is 1. Log of 4.86 to the base 4.86 is 1. So that brings us to a change. Will the base always be 10? No. It can be anything. But my problem is I only have a log table to the base 10. I don't have. You will change the base. Doesn't mean I will make a new log table. No. I have only one log table to the base 10. So tomorrow, if I ask you, what is the log of what is the log of 25 to the base 10? I can tell you. 25 is 2 digits before the decimal, minus 1 is 1, plus 0 point, characteristic plus mantissa. Without the decimal also it is 25. I will hold my sheet, 25 0. So 25 0 is 3979. So I will write it as 1.3979. 1.3979 is the answer. But what if I now ask you, what is the log of 25 to the base 5? I don't know. Because my log sheet only and only gives me logs to the base 10. It does not give me logs to any other base. But it's common sense. Isn't 25 the second power of 5? So what should I raise 5 to get 25? 2. That's it. Because 5 square is 25. Do I need a log table? I don't need a log table. So can I conclude here that I don't need a log table if my number A is a perfect power of the base B? Example, if I ask you log of 8 to the base 2, well, 8 is the third power of 2, then the answer is 3. I don't need a log table. If I ask you log of 625 to the base 5, is 625 a power of 5? Yes. Which power? Let's check. 5 into square, cube, raised to 4. Oh, fourth power? Then the answer is 4, because 5 raised to 4 is 625. Don't believe me? Check. 5 raised to 4 should be 625. Is this logic correct? Then this logic is correct. So the first declaration. Will the base always be 10? No. But if the base is not 10, I can't give you logs because my log table is to the base 10. But then again, I can give you logs if the base is not 10, but then the number should be a perfect power of the base. If it is the perfect power of the base, then I can give you logs. What if it is not a perfect power of the base? For example, what if I go ahead and ask you, what is the log of, let's say, 121 to the base 11? Well, this I know. See, I have a log table to the base 10. I don't have log table to the base 11. I can't create a new log table every time you change the base. Tomorrow you will say the base is 11.5. I will have to make a new log table to the powers of 11.5. But the thing here is, in this, it is special because 121 is 11 square. And that is why the answer here is 2. 11 raised to 2 is 121. Do I actually need to know, or do I actually need to have a log table with me? No. 11 square is 121. But what if I change this and I ask you, what is the log of 2 or 316 to the base 11? Well, this is a problem. You know why? Let's check what powers of 11 are. 11 into square is 121, which we knew. Cube is 1331. Do you agree that the powers of 11 when squared is 121 and when cubed is 1331? My number, which is 316, is between the two. Now the problem is, I can tell you one thing, that this answer should be somewhere between 2 and 3, so it should be 2 point something. But I can't tell you what the exact value is for a simple reason that I don't have a log table to the base 11. And this is where they came up with a solution for this problem. Meaning, if you ask me log of a number to a base other than 10. So let me take one more example, slightly different. If I am asked log of 463 to the base 15. 15, first power is 15, second power is 225, third power is 3375. So 15 square cube, first power is 225, second power is 225 and third power is 3375. My number 463 lies between the two. So again, my answer is going to be 2 point something. Problem, I don't know what the exact value is because your base is 15. If your base was 10, I could give you an answer. This is where a formula called the change of base theorem was introduced. What did the change of base theorem say? The change of base theorem said that it is not always that the base will be what you desire. It is not always the base will be what you want. So we have come up with a change of base theorem that will help you change the base and make it what you want it to be. Meaning, the change of base theorem said that if you are doing a log of a to the base b and you don't like the base b, then change it. Change it and write it as what? Anything you want. Anything you want. Just one thing. You will write it as log a divided by log b. You can change the base now and write any base you want to. Just one request. Whatever base is written in the numerator, same base has to be written in the denominator. So if you write x here, you have to write x here. If you can write 10, 10, 6, 6, 8, 8, 5, 5, 2, 2, 4.5, 4.5, 3.1486, 3. Anything you want. Just make sure whatever is written in the numerator, the same base is written in the denominator. So now if you ask me the log of 463 to the base 15, can I say that I am changing the base and writing this as 463 2 divided by log of 15. But sir, what is the base now? Anything that you want, anything that you desire. What do I desire? I have a log table to the base 10. Then I am going to change it and make it 10. So let's continue. Log of 463 to the base 10. 3 places before the decimal, minus 1 is 2. Point. Without the decimal, the number is 463. 463. So let me get the log sheet. Under 46, I have to look for 3. So under 46, I have to look for 3. The answer is 6652. So it is going to be, 665. 46 3 is going to be 6656. So it is going to be 6656 divided by 15. 2 places before the decimal, minus 1 is 1. Point. 15, there is nothing else. So under 15, I will look for 0. So 15, I will look for 0. The answer is 1761. So I'm going to say this is, I'm going to use a regular calculator to do this division. 2.6656 divided by 1.1716. So 2.6656 divided by 1.1761. The answer that you get is 2.2664739 and so on. So I'm approximating that to 2.2665 is the value of log of 463 to the base 15. But sir, I have a problem. How do I believe that this is correct? You will write down anything that you want to. I'm not going to believe that it is correct because you didn't do this with a log table to the base 15. You did this with a log table to the base 10. But let me tell you one thing. Didn't I tell you that 463 is between the second and the third power? So the answer should be 2 point something here. The answer should be 2 point something. But sir, I want you to verify it. I'll verify it for you. When you say that log of 463 to the base 15 is 2.2665, can I say what you mean is when 15 is raised to 2.2665, I get 463. Isn't that what it means? Yes, that is exactly what it means. Then let's verify. When I verify this in my calculator, I get 15 raised to 2.2665. What do I get? 463.0318. Isn't that approximately 463? Then isn't this logic correct? Then if this logic is correct, then mind you, this logic is correct. And if this logic is correct, this logic is correct. And if this logic is correct, this logic is correct. I want you to write down this entire explanation right from here. Right from here up till here. I want you to give it a heading called the change of base theorem. The change of base theorem. Write the entire thing down. Pause the video. Write the entire thing down. Let me repeat this quickly. We have a log table to the base 10, but it is not always that you are going to have a log table to the base 10. sometimes they might ask you a log to some other base. Then there are two ways of going about it. Method number one, if the number written is a perfect power of the base, like for example, if the number written is log of 25 to the base 5, well then 25 is the square of 5. 2 answer is 8 to the base 2. Well then 8 is the third power of 2. So 3. 625 to the base 5. I don't need a I don't need a log table. I don't need rocket science to understand this. That 5 raised to 4 gives me a 625. Then the answer is 4. But what happens when you ask me something odd, which is something like a log of 316 to the base 11, or the calculation that I have done, and that is the log of 463 to the base 15. Well, in such a case, if the base is not 10, I cannot find you the log using my log table. And the other problem is 463 is not a perfect power of 15, which is where I use a change of base theorem. The change of base theorem says that log of a to the base b is log a divided by log b. And what is the base now? Anything that you want. Here I wrote 1010. It wasn't compulsory to write 1010. I could have written 6644, 88, 3.5, 3.5, 14.2, 14.2, anything. But then what is more convenient for me? 10. That is why I wrote 10. And then I say that I change the base to 10. I find the value of the new log. And this is what it comes out to be. A little theoretical, it works out to be correct, I think, because I knew that the log of 463 to the base 15 should be somewhere between the second and the third power. So it should be 2 point something. So according to this, it is correct. But then I verify using my cell phone, and it also works out to be, this relationship works out to be correct. And this is the change of base theorem. So as of now, we have done three things. Number one, we have done what is the relationship between a, b and c. That is, if log of a to the base b is c, then b raised to c is a. Basically, I am asking you, what should I raise b to get the value a? Or a is which power of b? So a is the cth power of b. This is the logarithmic relationship between a, b and c. This is the exponential relationship between a, b and c. After that, we realize that if you are basically asking me what power should I give it, then in that case, if the number is a perfect power of the base, then I don't need a log table. I will directly write down the powers. Why do I need the log table? I don't need the log table for anything. I will directly write down the powers. The power here is 2, the power here is 3, and so on. Because 100 is the second power of 10, 1000 is the third power of 10. So you are telling me if a number and the base is the same, I am asking you which power of 10 is 10. Array, 10 is the first power of 10. 25 is the first power of 25. 14 is the first power of 14. So this is the second rule that we did, that log of a number to the same base is always and always 1. After that, we came to, what if now I ask you log of a number to a base which you don't identify and the number is not a perfect power of the base? Well, in that case, we have two methods of going about it. Method number one, check if it is a perfect power. No. If it is not a perfect power, then we use change of base, and using change of base theorem, we find the value of that log. And this is the answer. So we are deriving, or we are understanding one log rule at a time. So we don't have to mug them up. We don't have to by heart the log rules. We are going to understand them so that it's easier to recollect and bring them back. Also, I don't think you have written this also. So you are going to say, as far as the base is concerned, there are two types of bases. One is the base 10 and the other is the base e. Logs to the base 10 are called common logs, and logs to the base e are called natural logs. The logs that we use are common logs, or the log table that is given to us is the common log. Now, can I finish this off, or this part off, by saying one more thing? If you are given the log of a to the base b is c, correct? then what do we say? That b raised to c gives me an a. If b raised to c gives you an a, let's go with laws of indices. In laws of indices, if you have b raised to c, what is b called? The base, and c is called the index. But my point is, b is called the base, no? In logarithms, where does the b go? The b goes here. But isn't that the base? And that is why we call it the base. Log of a to the base b is c. These basics or these small questions are asked as MCQs. So I want you to understand what we are doing here. Mugging up formulas is easy, is okay, but if you don't understand what it means, then what's the point of mugging up the formula, or what's the point in knowing the formula but not knowing what it means? That is why I want you to understand whatever we are doing here. Now, the rest of the log rules that I want to do require you to understand anti-logarithms. So before we move on to anti-logarithms, or how to take an anti-log, which we are going to do in the sheet, I want to show you one fantastic thing that is going to drop your jaw. And that is, I want you to pull the sheet that we have taken logs in. Where did my sheet go? The sheet where we have taken logs. You must have written it in your notebooks. I had written it in my sheet, which is gone missing. You can take logs in your calculators. Yeah. How do you take logs in your calculators? It's a simple method. I'm going to show it to you, and then later we are going to write it down. So let me unzoom this a little for you. I'm taking examples that we've already done. So we are taking the log of 23.6 and the answer should be 1.3729. Correct? So let's do one thing. Before we actually find it, I want you to write this down in your notebooks. Humor me and write down whatever I'm saying, one step at a time. Finding log 2 base 10 in calculator. How do you find logs to the base 10 in your calculator? Step 1, type the number. Step 2, press the root sign 15 times. Sir, we did this when we were doing roots also. Correct. Same procedure. Type the number, press the root sign 15 times. Subtract 1. Sir, we did this also. Yes, correct. After this it changes. Here after this, we used to divide by what root you want to take. We are not going to do that anymore. We are going to divide by 0.0000 70 to 71. This is how I remember it. 70 to 71. It's not 70 to 71. 70 to 71. That's your answer. You can take a log of any number in your calculator, but if the base is 10, if the base is not 10, you can't do this in your calculators. I want you to come to the first page, pause the video and write this down, and I will show you how logs are taken. (23.6). Press the root sign 15 times. Correct? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Minus 1. Subtract 1. Divided by 0.000070 equal to 1.3729. 1.3729. It is correct up till the first 4 decimals. You're welcome. Thank me later. Pick up any random number. Let's say I'm going to find the log of 923.6. Find 923.6. So AC 923.6. Step 1, type the number. Step 2, press the root sign 15 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Subtract 1 from it. Divided by 0.000070271. Press equal to 2.96572. Is that right? 2.965. We got a 5, they got a 7. That's okay. It's like 1 or 2 unit change in the 4th decimal. So that is not a problem. So the answer is approximately correct. And this is how you can find any log, but to the base 10 in your calculators, not to any other base. If the base is 10, then only you can do this in your calculator. That's our common sense. Haven't we learned the change of base theorem? So then if you ask me anything, I can find you anything. Like for example, if tomorrow you ask me the log of 763.8 to the base 16.4. Well, I'm going to say I can't find this. I'm changing the base. This will be log of 763.8 divided by log of 16.4. What is the base now? Whatever you want it to be, I am writing it as 10 and 10. According to me now, you can actually find this in the calculator. You don't need to have a log sheet on you because the base is 10. So in your calculators, 763.8. 763.8. Press the root sign 15 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Minus 1. Divided by 0.000070271. What do you get? 2.88320274,366. 2.88320274,366. The whole divided by log of 16.4 to the base 10. Base 10 I can do in my calculator. 16.4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Minus 1. Divided by 0.000070271. What do you get? 1.214866 and so on. I'm writing this down. 1.214866588792. I'm going to divide the two. I'm not showing you the division. I'm directly doing it. 2.88320274,366 divided by 1.21486658,792. The answer is 2.37266,96801, which I am approximating to 2.37266. I am writing as 27 is the log of 763.8 to the base 16.4. But sir, how do I believe that this is true? Check, no? Check if 16.4 raised to 2.3727 gives you a 763.8. Let me check this in my cell phone. (16.4) raise it to 2.3727. Sorry. (16.4) raise it to 2.3727 equal to, you get a 762.88, which is approximately 763. So isn't this logic a correct logic? Yes, it is. And this is how you can find logs in your calculators. If you want to keep checking, if you want to practice, go back to your sheets and pick up random numbers and try to find the logs if they verify or they don't verify, and they will. What is the logic, or what is the calculation? Now see, what is the logic behind that calculation? Even I don't know. Don't ask. It's a shortcut that is being derived, so I don't know. You can find any log to the base 10, to the base 10, not any other base, only and only to the base 10 in your calculators, and this is how you do it. Check all these calculations using your calculator and then find out.